Yeah, is it audible?
Yes, sir.
Right. So let's start today. So as of now, what we have discussed, okay, let's list them. What are the basic gates we have? You can say what are the basic gates using which we can design any digital system. Okay, any digital system that can be designed using three different gates. What are they? First one
And
is AND gate.
or
Okay, and second one is OR gate.
not.
Okay, NOT gate. Right, these three are called as basic gates, and any digital systems can be designed using this gate, these three gates. Okay, some sort of combination of these three gates, right? But what we will learn today is, uh, along with these three we have learned few more gates. Okay, such as we call it as NAND. Okay, NAND gate and NOR gate. Okay, and XOR, XNOR. Okay, out of which this NAND and NOR, these two, we call it as universal gate. Okay, we call it as universal gates, right? So this universal gates means what? Any gates or any digital system can be designed using only NAND or using only NOR gates. Okay, so that's why these two are called as universal gates. Okay, these three are called as basic gates. Universal gate means what? We can use NAND gate only to design a given digital system. Okay, or any digital system by using only NAND, it is possible. So today we will learn that. Okay, so today what we will learn? We will learn NAND as universal gate. Okay, so today we will learn NAND as universal gate. Okay, NAND is universal gate. So in this, first let's learn, okay, how we can use NAND, okay, as not gate. NAND as not gate. Okay, NAND as not gate. So if you have two input A and B, okay, what is NAND? NAND is A, and with B it's complement, right? Isn't it? So if this is 0 0 0 1 1 0 1 1, so what we will get? 0 0 means 0, and with 0, that is 0, its bar is 1. 0 1 0, answer is 1. Okay, so here also it is 1, here it is 0, isn't it? This is NAND logic. What is not logic? Not logic is if A is given, okay, so you will be getting A complement, right? If this is 0, this is 1. If this is 1, this is 0, right? So this is NAND logic, this is not logic, right? So if A and B are the inputs, right? If A and B are the inputs, how we represent? Using NAND. This is NAND. Okay, this is NAND gate. If you give A here, if you give B here, what we will get? We will get A, and with B its complement. That is A NAND with B, right? So how we represent this gate? This is not gate. Okay, if you give A, you will get A complement. If you give B, B complement, right? Now how to realize this gate? How to realize this not gate using NAND gate? Okay, how to make a not gate using NAND gate, right? So if you give A, if you give B, okay, if you give here A, if you give here B, what we are getting here? A dot B bar. Okay, A dot B bar. Now what I will do, I'll just make some change here, right? And see, this is the NAND logic, right? Instead of A, I am giving A. Instead of B, I am giving, sorry, A only, right? So what I will get here? A and with A bar. What is A and with A? A and with A, what is the answer? 0 with 0 is 0, 1 with 1 is 1, right? So A and with A is what? A.
A.
It is giving A complement, right? So you can observe here, right? This gate and this, the function is same, isn't it? So NAND NAND gate can be used to realize NOT gate. So rather than using this basic gate, okay, NOT gate, I can use NAND gate. There is some reason why we take always NAND and NOR logic, okay, compared to basic gates. In subsequent classes, we will learn that, right? So it helps in designing circuit, okay, integrated circuits. Okay, that's why it is helpful, right? So first learn today NAND as NOT gate. Okay, so this can be drawn in this way also, right? Okay. So if you give here A, you are getting A bar, right? It's the same thing, right? Same thing. So first one we have learned NAND as NOT gate. Okay. Now let's learn second one. All of you remember this. Okay. So this is equivalent to NOT, right? Now next we will learn NAND gate as AND. Okay. How to get AND out of NAND? Okay. So if you have A and B as input, if you have A and B as input, right? And if you give them to AND gate, okay, and if you put a NOT gate over here, what we get? We get what? A and B complement, isn't it? A and B complement. This is what? Which logic? This is NAND logic, isn't it? And with a NOT gate, okay, and with a NOT gate is NAND. We would like to make AND gate, okay, we would like to make AND gate using NAND gate. Okay, how to get AND? If you put an inverter to AND, it becomes NAND. If you put an inverter to NAND, it will become AND. Okay, so if you have NAND gate, okay, and I put one inverter here, okay, so what I will get? I will get AND logic, isn't it? I will get AND logic. So what we will do? We will take this input here, okay, A and B, and this is NAND, isn't it? A, B. So output is what? A dot B bar. Now I would like to put an inverter here. Okay, I would like to put an inverter here so that I will get A dot B, right? So what we can do here? We want the whole thing should be realized using NAND logic. Okay, so this inverter, okay, need to be replaced with NAND. How to invert? How to replace inverter with NAND? What is the figure? Okay, this inverter I would like to replace. We have just learned. Okay, how to do it? This one, okay, or this one, blue color one. Okay, right? We'll do this thing. So if you give the same input to both in a two input NAND gate, we will be getting the complement, right? So what we will do here? So this is okay. This is A, B, then what we will get here? A and B, right? So this is what? Okay. This is what? AND gate realized
AND gate.
NAND gate. Okay, AND gate realized using NAND gate. So now onwards, whenever AND is required, we will be using this. Okay, rather than using this gate. Okay, we will be using this gate. This is A, B. This is A and B, right? So if you are asked that realize and logical operation using NAND, so what you have to do? You have to do this. Okay, not this one. Okay, so this is basic gate. This is basic gate. This is realized using NAND logic. Okay, so now onwards, whenever NAND is required, we will be using this, right? We will be using wherever AND is required, we will be using this, right? Now let's learn the third logic. Okay. So we would like to make NAND, okay, as OR gate. Okay, NAND as OR gate, right? NAND as OR gate. So let's see. Two inputs are there. Okay, two inputs are there, A and B. If this is NAND gate, what output we will get? A dot B bar, right? So what is A dot B bar? De Morgan's law, if you put, what is this? A dot B bar can be written as A bar plus B bar, right? A complement or with B complement. So if you give two inputs A and B to NAND, what we are getting? OR of complement of those two inputs. Okay. So what if I give here A complement and B complement? What I will get here? What I will get here? I will get,
A plus B.
okay, A plus B. That is A plus B means what? This is OR. Okay. So when I replace A with A complement, B with B complement, what I am getting? A or with B, isn't it? So let's implement this. Okay, let's implement this. So how we can do, right? So how we can do? I want A complement at the input. So I have A here, A complement. Okay, I have B here. Okay, that, let me write here. This is A complement. This is B complement. And if we take this two, okay, we take this two and give it to NAND gate, what we will get? We will get A or with B. Okay, we will get A or with B. Okay, isn't it? A or with B, right? Now let's replace this AND gate. Okay, let's replace this AND gate. Okay, using NAND logic. So what we can do? AND. How to replace NOT gate with NAND gate? How to replace NOT gate with NAND gate? So what we have to do is A is the input. Okay, this is A complement, right? B is the input to give the same input to NAND gate. This is B complement, right? If we give it to this is A, B. Is it correct? Okay. So what is this? This is OR gate realized with NAND gate. Okay, this is what? OR gate using NAND logic. So whenever now we require OR gate, okay, we can use this thing, right? We can use this thing. Okay, so we have learned what? As of now, we have learned how to make NOT gate using NAND gate, how to make AND gate using NAND gate, how to make OR gate using NAND gate. Okay, how to make, this is 3. Okay, so NAND as OR gate. Okay, see this figure is what? This is AND using NAND. Okay, this is AND using NAND. Right. The first one we have learned is this is second one. This is the first one. Okay. This is NOT gate. This is AND gate. Okay. This is AND gate. Right. This is AND gate. And using NAND. Recently we have learned what this third number is. Okay. OR gate using NAND gate. Okay. Now let's learn. I would like to make XOR gate. Okay. I would like to make XOR gate using, I would like to make XOR gate using NAND. Okay. What is the expression of XOR? If you have A as one input and B has another input, okay, two input. What is A XOR B? A XOR with B. Okay. What is the logical expression for this? This is AB bar plus BA bar, isn't it? Right. So what you will get? This is 0 0. Let me write the truth table. This is 0 1 1 0 1 1. What you will get for XOR?
1001.
When two inputs are same, okay, when two inputs are same, output will be,
Same.
okay, 0, right? So this is 0 0 complement plus 0 0 complement, so it's 0. If both inputs are same, we will be getting output 0. If inputs are different, you will be getting logical 1. Okay, so in order to implement this expression, okay, in order to implement this expression, this is what logical expression of A XOR B, right? A XOR B. How many NAND gate, how many AND gates are required? How many AND gates are required? Two AND gates, right? How many OR gates are required? One OR. How many NOT gates are required? Two NOT gates. Okay. So in order to implement this, two AND are required, one OR is required, two NOT are required. Okay. Now, in order to implement AND gate, how many NAND gates are required? See here, this figure. Okay. In order to make AND gate, how many NAND gates are required? How many? Two, isn't it? This is one, this is one. Two NAND gates are sufficient. Okay. So for making AND, one AND, two NANDs are required. Okay, two NANDs are required. And to make one OR, how many NANDs are required? Three NANDs are required. Okay, three NANDs are required. So let's make a conclusion here. Okay, so for this, how many NAND gate is required? 4 NAND gates are required. Okay, to make one and 2 NAND. Okay, this is 3 NAND gates are required, and for this we require for 2 NOT gate 2 NAND gates. So totally how many NAND gates are required? 9 NAND gates are required, isn't it? In order to implement or make this logical expression using only NAND, we require 9 NAND gates. Okay, 9 NAND gates are required. Okay. So let's see this. Okay, let's see this. So how to make? So the expression what we would like to implement is a b bar b a bar. Okay, so a b bar plus b a bar, right? So what we have to do first? This is a, so we will get a bar here. Okay, this is b, we will get b bar, isn't it? B bar. Then we used to have some AND gate. Okay, AND gate which require 2 input. Okay, one is this, and here again another AND is required. One input is this. Okay, so here input is a bar. Okay, a bar, another input is b. Okay, another input is b. This is b. So here let's take, what do you get? A. So what is this AND gate output? This is a complement b. This is a b complement. Now we take this two and take an OR gate. Okay, so we will get a bar b plus a b bar. Okay, a bar b plus a b bar, right? This is same, right? A bar b plus a b bar. Okay, so this is a bar b, this is a b bar. Okay, right? So let's replace this figure with pure NAND. Okay, so how to do this? You can say how we can do this. We'll say B956, B956, B956.
56.
Are you there? Okay, madam, note
He
down.
is there, sir, but not responding.
We'll make him absent. We make a note of this number.
Absent.
B9 roll number 7, Shivam. B9 roll number 7. $11.
Yes, sir.
Yeah. Can you say how to do? Pick.
Sir, first to make it not a, we have to do NAND, sir.
Okay, right. So if we have A here, right? Let's replace this NOT gate with NAND gate.
NAND.
So let's replace this NOT gate with NAND gate. So this is A bar. So if you have B, let's replace it. Okay, this is B bar, right? Now we will be replacing this gate, okay, and this gate by the NAND gates. To replace one AND gate with NAND gate, okay, what is the circuit?
Two
Replacing,
NAND.
okay, two NANDs are required, right? Two NANDs are required. Okay, so let me show you again, right? This is the figure, okay? This is the figure for if you give input AB, output is A dot B, okay? This is the figure, right? If you take AB with a NAND gate, so output is what? A dot B bar, and if you again invert it, you will be getting A dot B, right? So let's put this logic here, okay? Right? So for one NAND gate, what we'll do? What are the two inputs required for the NAND? One input is this A complement, okay? Another input is B, okay? Another input is B. So let's take a wire from B, okay? Let's take a wire from B. Let me take it in some another color. Okay. Now we'll put it through a NAND logic, right? So output is what? This is B. This green color thing is B. Okay. So output of this is nothing but A bar dot B. Okay, it's complement. Okay, A bar dot B, it's complement. Okay. Then if you take complement, right? What we will get? We will get A bar dot B. Okay. Similarly, for this, we will take another NAND gate and let's take A. Okay, for the same purpose. Right. So this is A. Okay, and this is B bar. So what you will get? A dot B bar, its complement, and I take an AND here. Okay, so what it gives me is A dot B bar. Okay, now what is required? We have to replace,
Okay.
okay, this OR gate. Okay, we have to replace this OR gate, right, over here. Okay, in this space, right, we will be making that OR gate. Okay, so let's see how to make that. OR gate require how many NAND gates to be realized? Let's see the figure again. Okay, for OR gate, see this figure. So if A and B are the input, okay, we have to invert A and B and then pass it through a NAND gate that will give us OR operation, right? That will give us OR operation. Okay, so let's do it here. Right. So this is one input and this is another input. You have to invert them. Okay, so we have to invert them. So how to invert each input? Okay, so this is an inverter and this is another inverter. Okay, I guess it's not clear enough. Okay, let me erase this. Okay, so let's take this. This is one inverter. Okay, this is another inverter. Right, two inverter. Then these outputs should be given. Okay, NAND logic. Okay, so this is okay. What is this? This is A dot B bars bar. Okay, so output what you will get is okay. Right. So I have written here directly. Okay, so actually what we will get here, NAND of these two values. Okay, NAND of this value and NAND of this value. So what you will get? NAND means right. NAND means this. Okay, this is one term. Okay, and with A dot B complements complement. Okay, it's whole complement. Right? If you solve, you will be getting this. Put De Morgan's law. Right? Okay, is it clear to all of you?
Yes, sir.
Right. So similarly, we can you can try the exclusive NOR. Okay, you can try exclusive NOR. Okay, using NAND. Exclusive NOR using NAND logic. Okay, so how to get exclusive NOR using NAND logic? You can take exclusive OR. Okay, and follow it with inverter. Okay, so you will get exclusive NOR. You will get exclusive NOR. So you can complete this task. Okay, this is not much difficult, right? NOR means what? Exclusive OR we have uh, already done now, and this can be replaced by this gate. Okay, this will give us X NOR. This will give us XNOR gate. Okay. So this in place of XOR, okay, we can put this one, this figure. Okay, we can put this figure. Okay. I guess we can reduce the number of gates that can be used here. Okay, we will be learning it later. You can see in this figure, right? You can mark here this value, okay, and this green colored value. They are same, isn't it? They are same. So we can remove these two gates, okay, and directly connect it. It will give the same logical expression. Okay, that can be done. Okay, right. So I leave it for you people to do the exclusive NOR using NAND. Okay, so next class we will be learning all these gates. Okay, what we have learned today, that is starting from NOT gate, okay, AND gate, right, and OR gate, right, XOR gate, NOR gate. These all gates we will be designing using NOR logic. So we have learned today this all gate designing using NAND logic. Okay. So next class we will be doing it using NOR logic. Okay, you can try this. You can try this as homework. So we may include it in the exam. Okay. It is very easy, and I leave it up to you to try this as homework. Okay. Right. So next class we will be having exam. Okay, on coming Tuesday. Date is, I guess, 13th, right? Tuesday. Date is how much? 13th. Okay. Date
13
is
only, sir.
13th October. Okay. Timing around 2 o'clock. Okay.
Sir, what is the syllabus for the unit test module?
Unit test syllabus is unit 2 complete. Okay. Completely unit 2. Right. So all the relevant lectures will be loaded. Okay. By today evening. Right. I will make it short enough so that you can learn quickly. Right. So you can assess the YouTube channel or Google Classroom, right? So be prepared for the exam and perform well, right? So complete this part using NOR logic. Okay, how to realize all the gates, right? Any queries?
Sir, will there be any